Hello everyone and welcome back. If you're ready to learn and kind of eager to understand how machines actually make decisions, well, you are in the exact right place. Today's explainer is all about a massive, truly foundational pillar in the world of data science, logistic regression. We're going to build your understanding of this incredibly powerful algorithm completely from scratch. So, by the end of our time together today, you'll understand one of the most widely used algorithms in all of machine learning, one that's literally working silently behind the scenes in almost every app and service you use.
To get us started, I want you to think about your email inbox for a second. Every single day, your email provider receives messages and has to make a split-second decision. Should this incoming email go straight to your primary inbox, or should it be banished to the junk folder? Have you ever wondered how a computer actually decides if something is spam or not spam?
Or, consider a setting with much higher stakes, like a hospital. A doctor inputs a patient's medical data into a diagnostic system, and the computer evaluates it to answer a really critical question. Does this patient have a specific disease or no disease? Predicting yes or no is the absolute core problem we're solving today. It's called binary classification, and it is an entirely different beast from just predicting a number.
Okay, let's look at our roadmap. 1. Beyond linear, predicting categories. 2. The magic sigmoid function. 3. Making the prediction. 4. Rules and trade-offs. And 5. Real-world applications.
Starting off with Section 1, Beyond Linear, Predicting Categories.
So, if you're familiar with basic statistics, you've probably heard of linear regression. It's your go-to when you want to predict continuous values, right? Think of things like estimating a future salary, predicting the price of a house, or guessing tomorrow's temperature. The output can be literally any number, infinitely large or infinitely small. But sometimes we don't need a continuous number, we need a specific category. That's why we have logistic regression. Now, I know what you're thinking. It has the word regression in its name. Honestly, that's just a bit of historical baggage. Logistic regression is strictly for classification. It predicts categories, yes or no, fraud or not fraud, spam or not spam. It limits its output to a strict probability.
Moving right along to Section 2, the magic sigmoid function.
Meet the sigmoid function. This is the mathematical heart of our algorithm that makes binary classification even possible. Now, don't let the formula intimidate you. I want you to think of this not as complex math, but as a really cool machine. You can feed this machine any number in the universe, positive a million, negative a million, whatever you want, and it will perfectly convert it into a probability exactly between 0 and 1. When the input, which we call z, is very large, the machine's output gets closer and closer to 1. When z is very small or negative, the output approaches 0. When you graph this all out, it creates this beautiful, elegant S-shaped curve. This curve right here is the absolute secret sauce of logistic regression.
And right smack in the middle of that S-shaped curve is a very special number, 0.5. When the input fed into our sigmoid machine is exactly 0, the output is exactly 0.5. In the world of binary classification, 0.5 is our magical threshold. It's the exact tipping point where the algorithm stops leaning towards no and starts firmly leaning towards yes.
Which brings us perfectly to Section 3, making the prediction. Let's see exactly how the algorithm uses that magic threshold to make a final call. Making a machine learning prediction here is really just like following a super simple 3-step recipe. Step 1, you calculate a linear combination of your inputs. Basically, you take your data, say a patient's blood pressure and age, multiply them by specific weights the model has learned, and add them all up to get a single number, z. Step 2, you take that number z and pass it through our magical sigmoid function to get a nice clean probability between 0 and 1. And step 3, you check the threshold. If that probability is greater than or equal to 0.5, the model boldly predicts class 1, like yes, spam. If it's less than 0.5, it predicts class 0, not spam. It really is that straightforward.
What's totally fascinating here is how we can visualize that exact decision geometrically. By using that 0.5 threshold, logistic regression draws a literal line in the sand between two groups. We actually call this the decision boundary. If you're looking at a 2D graph with two variables, it's a straight line separating the safe credit card transactions from the fraudulent ones. If you have 3 variables, it becomes a 3D plane. The algorithm mathematically maps probabilities on either side of this boundary to make its choice.
But wait, how does the machine actually learn to draw that line in the perfect spot? Well, it uses a scorecard. Specifically, something called binary cross-entropy loss. If the model is super confident an email is spam, but it was actually a vital message from your boss, ouch. This scorecard heavily penalizes the model for that. The formula simply measures exactly how far the predicted probability is from the actual true class label.
Then, through a steady, step-by-step process called gradient descent, the model continuously adjusts its weights to get a better score, essentially learning from its mistakes until it draws the perfect decision boundary.
All right, time for Section 4, Rules and Trade-offs.
So, no algorithm is perfect for every single situation, so let's get real about the trade-offs. On the pro side, logistic regression is incredibly fast and simple to train. Also, it doesn't just give you a blind yes or no, it outputs actual probability scores, which is massively useful for making business decisions. It's also highly interpretable. You can look directly at the math and see exactly which features are driving the decision. But take a look at the cons. It absolutely cannot solve complex nonlinear problems. If your two classes are swirling around each other in a circle on a graph, yeah, a straight decision boundary line isn't going to help you. It's also pretty sensitive to extreme outliers, and it genuinely struggles if your data categories heavily overlap.
Because of this, the crucial point to remember is that before you trust your model, your data has to play by these specific rules. We call these assumptions. First, the outcome variable must be strictly binary, 0 or 1. Next, the observations must be independent, meaning one data point doesn't influence another. You also shouldn't have multicollinearity, which is just a fancy, intimidating way of saying your input features shouldn't be too strongly correlated with each other. And finally, you generally want a large sample size so the model can stabilize its estimates. If you break these rules, your model's predictions might just fall apart completely.
But if your data is ready to go, implementing this is wonderfully simple. In Python, using the scikit-learn library, it takes essentially 4 foundational lines of code. You import logistic regression, you split your data into training and testing sets so you can evaluate it honestly, you call model.fit, and this right here is where the actual machine learning and gradient descent happens, and finally, you call model.predict to let the algorithm classify new unseen data. Just 4 lines. It is beautifully concise.
Let's wrap things up with Section 5, Real-World Applications.
Let's see how this incredibly elegant code is actively powering the modern world. Logistic regression might be simple, but I promise you, it is everywhere. Beyond the spam detection and disease diagnosis we talked about earlier, it's basically the bedrock of the financial sector. When you swipe your credit card, a logistic regression model is very often the first line of defense predicting if that transaction is fraud. Marketing teams use it for customer churn prediction, constantly asking, will this user cancel their subscription this month? It's even used in basic product recommendations to predict if you'll click on a specific item or not. And what's truly amazing, that simple sigmoid function we just mastered is the very foundation of complex deep learning and massive neural networks used across tech and cybersecurity today.
So you now understand exactly how a machine draws a mathematical line in the sand to make a binary choice. But what happens when the decisions get a lot more complex? What happens when a simple straight line just isn't enough? Are you ready to see how machines learn to make decisions that actually mimic human logic? Because that is exactly what we're going to cover in our next explainer on decision trees, which takes these foundational concepts to an entirely new human-like level. You really won't want to miss it. Keep learning, stay focused, and I will see you in the next one.